So there won't be any data loss. Okay, try to find out. I'll ask one by one. Yeah, so anyone?
Why a minute, sir?
Okay, no problem. Take your time. This type of question they may ask in the interview, and in an SOC point of view, we have a lot of FIFOs in the middle to avoid those kind of data loss. So that's why I asked this question.
We write the answer inside the chat box, sir.
Just tell me, okay. So man then wrote 75, Wu wrote 192. Who is Wu? Wu. The total
Yeah,
data items are 120. Why we need 192? The minimum
uh,
depth. Why we need 192? Because the total data items are 120. So the maximum depth is 120. You store everything in FIFO and read it back.
yeah, because
Now,
I think it write and read in just in one clock.
write in one clock, read in the one clock. Yeah. So FIFO is used to store data in the middle, right? That there shouldn't be any data loss because the writing frequency is faster than the reading frequency. NAM, why 192? Total data items are, yeah, NAM, you change your answer to 75. That is also wrong.
Okay, sir.
NAM, try it again.
Yes, sir.
Wu, you also try it again. 192 is the wrong answer. Maximum is 120. The total data is 120. How come we store 192?
Yeah, yeah, sir.
Who is that? Yeah, that. Why
Yes, sir.
73? 73 is wrong. Try it again.
Yeah, yes, sir.
I will talk to Wait. Wait, Tran.
Yeah.
Yeah, Tran. So your answer is 45. How come you reached 45? Same with Huang.
I use the Westland time with uh, read frequency divided by writing frequency.
Okay. So what is the writing frequency?
80.
So to write 120 data items, how much time it will take?
Uh, 12.5 nanosecond.
12.5 nanosecond. And to write 120 for writing one is 12.5 nanoseconds.
Yeah.
Okay, so everyone tried or you want more time? I will explain the answer.
You can explain the answer, sir.
So
No, take your
give
time.
us
Take your time.
1 minute, sir.
5 more minutes. Take 5 more minutes, okay? Man, you also take 4 minutes.
Okay.
Okay, how? You can leave. Yeah, so the final answer everyone can type. Man is 53, Wu is 45, Dat is 74. 45. Now everyone is 45. So the correct answer is 45. Okay. So anyone wants to know the reason why it's 45? Or you are okay? You all got the answer 45. Man, the answer is 45. So it's very easy actually. So writing frequency is 80 megahertz, right?
Yes.
Right. So to write one data item, it takes 1 upon 80 megahertz is equals to 12.5 nanoseconds. Okay. To write 120 data items, it will be 120 cross 12.5 equal to 3000 nanoseconds. To read one data items, it takes 1 upon 50 megahertz. So it would be 1 upon 50 is 20. So 120 into 12.5 is 1500, not 3000. It is 1500. And while reading 1 upon 50 is 1 divided by 50 is 20 nanoseconds. 1500 divided by 20 divided by 20 is 75. Okay. So shift enter 20 nanoseconds and 1500 divided by 20. The total items that can be read is 75. 120 minus 75 is equals to 45. You see, I typed the answer. So the total writing time is 12.5 nanosecond for single data item. We need to write 120, so it's 1500 nanoseconds. And if we take reading time is 1 upon 50, so in 20 nanosecond you are reading one item. In 1500 nanoseconds of write, we read 75 data items. So the remaining 120 minus 75 is 45. So 45 is the depth of the FIFO. Got it? Everyone?
Yes, sir.
Yeah.
Got it.
Okay,
Got it.
Yes, sir.
try to solve these kind of puzzle questions, okay? It's important. Okay, so now let's start our class. I'll share the screen. I'll share my entire screen, so it should be good for you. So yesterday class was good. You understood something?
Yes, sir.
Yes, sir.
So this everything is clear how an SOC looks like, what is configuration space, what is the data space, and how the addresses are allocated. Everyone got it?
Yes, sir.
Yeah, got this, sir.
Okay, today we will deep dive more into this register. Okay. I will deep dive into this. Okay, let's start with this. So, like what? Okay, this is the plan. Actually, I will discuss about this register access today. Okay. And IO muxing. So these two topics we will cover today. Okay, so talking about the registers. So like what I told you, there are 32-bit registers inside any of the SOC. I mean any of the IP of an SOC. Okay. So there are a lot of 32-bit registers. And the address we already find out. So the minimum address will be 0000 and it will be 0FFC. So suppose the address of first is 0000 and the last okay. So, and yesterday we discussed about this, how the addresses are allocated. This one that we just extended it with some address extension value in in order to differentiate between the IPs of an SOC. So there are several registers, okay, inside, and each register have its own dedicated functionality. Okay, it means that if you write to register number 0, it tells to enable the device, to enable that IP. If you write to register number 1, it tells to send a command towards the slave. Okay, if you write to register number 3, so it tells about the speed mode on which the device is working. So there is a separate functionality allotted to each of the register block. Okay, so there are several registers like what I've told you, like this IPs. There are too many IPs, right? So there would be several registers present inside those IPs. Okay, so do you see my screen?
Yes, sir.
Yes, sir.
So this 1 minute, I have a call. Yeah, so yeah, this one. So there are several registers and okay, you see? These are all the IPs of an SOC. There may be thousands of IPs in an SOC. These are all IPs of an SOC that I'm showing you. Okay. And you see these kind of addresses we have seen yesterday, right? It is starting from 0, then it's 4, 41, 42, 43, 44, 4C, 4D. Like, right? We have seen yesterday these kind of addresses. So if you click any of the IP, you see there are several blocks. These are all IPs. And when you suppose enter this, these are the registers of these IPs. This is the first register, this is the second register, third register, fourth register, and each register have its own dedicated functionality. Okay, so you see a 32-bit register 0 to 31 value has been stored, and this is the address of this register. So if you want to access this register from in an SOC, so from any master, if you will issue this address, this will be targeting this register. Okay, suppose if we want to target this register, you see the address is 1008, so the data would be written in this register. So coming back to our drawing, so there are several registers present inside an IP. So now, so there have been an access rights for each of the register. The registers can be read only, the registers can be write only, the registers can be read and write. Okay, the registers can be write one to clear, the registers can be read to clear. Okay, sorry. So there are several access rights for each of the register blocks. Okay, if we talk about this,
Yes, sir.
so suppose all the blue registers that I have marked are read only registers, That means if you can only perform a read operation to those registers through an APB. Okay. The purple register that I am marking are the write only register. You can only perform write to those registers. You cannot read it. If you read it, it will just give you zero data. Okay.
Yes, sir.
Yes, sir.
Yeah. The light orange registers that I am just marking here are suppose read and write registers. So what you can do, you can perform a read to it, you can perform a write to it. Okay. This green register is suppose write 1 to clear. If I want to clear this register or the bits 32 bit of that register, I will write 1 to that particular value. Okay. Let's take an example. Suppose this register, I'm talking about this green register. Okay. So suppose this register have value A050 F0 F0 and you want to clear this register. What value you will write? You will write the same value. Okay. If you will write if you will write the same value to this register, what value you will write? A050 F0 F0 through APB. The value of this register now will be 0. Got it? So this is an example of write 1 to clear register. So I will write it like this. After writing this, the value will be 0. Okay. This register is suppose read to clear register. This dark red register. So if you will write, if you will just read the value of this register, the register will get cleared. You understood?
You read it
Yes,
to
sir.
empty.
We won't clear it. If you read it, automatically the register will get cleared.
Okay, sir.
So I'm pasting this beautiful diagram over here. So now you understood about the access rights. So if anyone asks you, so it will be read only registers, write only registers, read and write registers, write 1 to clear registers, read to clear registers. Okay.
So, sir, in read to clear register, so it have the data in initialization.
Okay. Okay. So what happens? Real-time data of the IP has been stored in that. Suppose these IPs have several counters. Okay. When you draw an IP, there are several internal counters used for debug features. Like what in VIP, if you have worked on, you have several internal logics that you had written, several counters and several values. Okay. So in the IPs, there are several internal counters been running, several internal values being used for debug purposes. Okay. So real-time values of those values been stored in this read only registers. Okay. So suppose for an example, you want to send 64 kilobyte of data through SPI. Okay. You just trigger the SPI and write it to the data register and start sending the data. Okay. Now when you will observe it, how many bytes has been copied. So you can just read this register to get the real-time value that okay, 64 KB of the value, 64 kilobyte I need to copy, only 20 kilobyte been copied, 21 kilobyte been copied. So from time to time, you can just read this register, and when you will read it, the value will get cleared, and the IP will go and write it again. The IP, internal IP. Okay, so these are the registers. Let's take the copy of this. Control C, Control V. Sorry, Control C, Control V. Okay. So these registers can be accessed by two things. So suppose this is a okay, this is the IP that have that registers. Okay, IP. and secondly, it from the outside world. So from the outside world, you access those registers through APB, okay, or AXI, anything. And
ABB
internally,
ASI HBM
HBM,
ASI sir.
AXI you can use, APB you can use. So, and these value of those registers been updated by RTL also. Got it?
Yeah.
From time to time.
Yes.
RTL can also update it, you can also update it. So both of the have those access right to these registers. So IP update those values from time to time, and when you update these registers, these values get reflected inside the IP from time to time. Okay. Suppose if you write to this register to enable something, then ultimately that value will be visible to the IP. Like this I can have to all the registers. So all the registers has been connected to the IP. So IP can write to them, and those registers can also pass their values towards the IP. Got it?
Yes sir.
So
Yes,
now
sir.
you have an idea about the registers, how the registers look like and how the things go on, right? How we are writing the IP, how we are controlling the IP. So all the IPs that we are using have these registers, the config space and the data space, and inside the config space, it has these registers. The config space has been accessed by an APB. So let's move further. I will take one more example. Okay, then how these IPs are integrated inside a SOC. So suppose this is a network on chip, NOC or NIC. We call it as NIC, NOC. Okay, so basically, if this is a CPU connected over here that is acting as a master. Okay, so okay, so any of the IP that is connected towards the NOC will have two interfaces. This is the IP. So it will have two interfaces. One interface is APB and one interface is another interface is
ASI.
ASI.
yeah, like what we have. I mean, so many. This is APB, APB, and this is AXI. Okay, this is CPU. Okay, so CPU only have, talking about ARM CPU, it only have AXI. It only have AXI interface. Okay, so can anyone tell me if we want to access APB or AXI, how does it differentiate? But because CPU only have AXI and but your IP have APB and AXI. So how we are accessing the registers?
Yeah, it did have a bridge for SXI to APB inside
Great.
the.
Yeah.
Yeah.
So first of all, you will send that address. Already we have the address map of config space and data space. So depending upon the unique address that it will generate, it will decide that, okay, it's a configuration space address or the data space address. Okay. And then internally that AXI transaction will be converted to APB and it will be written into the configuration space. If it is a data transaction, then it will be transmitted to this EXI interface. Got it?
Yes, sir.
Yes, sir.
Okay. Okay. Now I think you understood about this register access. Register access is clear?
Yes, sir.
Yeah, it clear, sir.
Okay, so
Yes.
this register access, now talking about IO muxing. So in this diagram, we talked about these IO pads, right? And someone asked me that day, what are these IO pads where they are used? So let's talk about them as well today. I will pull this out over here, okay? Okay, talking about these IO pads now. So basically, what we can say, you have seen an FPGA? Anyone of you have seen an FPGA?
Yes, sir.
In an FPGA, you have seen the pins, right? From where you are connected, you are connecting the LEDs or some external electronic device, right? FPGA have those kind of a pins, correct? Let
Yeah.
me open a diagram of an FPGA. Very basic. I will take vertex 4. Okay. Vertex 4. GPIO pins. Okay. Where can I see? Okay, I will show you like this. SOC GPIO pins. Okay. So, I mean, yeah, in an FPGA, you have seen these kind of a pins, right? These kind of a pins that are coming out. So they act as an GPIO. GPIO basically stands for General Purpose Input Output. Okay? GPIO basically stands for General Purpose Input Output. There can be many GPIOs in an SOC depending upon the requirement. Depending upon the requirement. Okay? The basic structure of a GPIO, I can say GPIO, as the name suggests, is general purpose input output. It means it can act as an input, it can act as an output. So there is a, if I talk about a GPIO, so I will take this line. Yeah. So it can have data from the outside world, and that outside world data will be transmitted towards the SOC, or it can pass the data, incoming data from an SOC, and it can pass it on towards the outside world. So this is your SOC, okay, and Control Z. This is your outside world, okay. This is your SOC and this is your outside world, and this is GPIO in yellow. So you can either pass the information from the outside world towards an SOC, and you can just pass it on like this. And it depends that whether your GPIO act as an input and output. So there is always a select. There is always a select line that decide whether your GPIO is acting as an input or acting as an output. Okay, got it? Internally,
Yes.
okay. So now bifurcating it more further, it have a multiplexer over here. It have a multiplexer over here. So what everyone knows, what is a multiplexer? It convert many inputs into one, like this. Yeah, sorry. Okay. And there would be a Control Z. Okay. So there is an input multiplexer. I can write input mux. Okay. So like what you have seen, okay,